All right, can you guys on Zoom hear me? Okay. All right, you guys far back, how well can you hear me right now? Good? Okay, shouting is gonna be the procedure because the microphone is broken. So without further ado, today is Intro to Reverse Engineering. Briefly about me, I'm a second year CS major here at UF. I enjoy reverse engineering and good typefaces and occasionally do security research, which is in quotes until I find something that I think is legitimately impactful. I'm going to start off with a series of questions. I expect everybody to raise their hand so we can all have a good time. How many of you guys here have ever used cheats in a video game or jailbroken your phone or used pirated software? Almost everybody, good. How many of you know what a compiler, disassembler, debugger, or assembly language is? Decent chunk as well. And if you had to rate yourself, I guess, number of fingers in the air, rate yourself with your comfortability with reverse engineering, because I can adjust the pace of this as needed. 5, okay. 2, okay, good. So you guys, you know the right audience here. So the reason I actually asked questions 1 and 2 is because 1 is kind of how you have benefited from reverse engineering, and 2 is kind of the backstory behind how you likely were able to jailbreak your phone or use cheats. And we'll see how these are related in a moment. Also, who hates being asked questions as part of presentations? 1, 2, couple, good. So reverse engineering is essentially analyzing software without source code. Obviously, if you have a program that you wrote yourself, you can easily just read through the code and see what it's doing. If you're trying to reverse engineer, you don't have the luxury of seeing the source code. So you're going to have to use special tools. In all of these scenarios, the main objective is to understand how a program works. Why you would want to do this is a fair question to ask. And the answer to that depends on a number of different things. So one main use case of reverse engineering could be verifying that software is safe. If you download something off the internet, you might not know exactly what it does. Obviously, you're not given the source code to a lot of programs you download. So you might want to reverse engineer it to determine if it's safe or see what it's doing. You may be hunting for vulnerabilities in a program that you can exploit to achieve a number of different things. In the case of jailbreaking a phone, you might want to find a vulnerability that can give you local privilege escalation and bypass other types of checks. If you're trying to land an exploit on Windows, similar concept. One example that most of you will probably be familiar with is if you've ever used cheats in a video game, that required somebody to reverse engineer the game to understand how different data is stored internally and how they can manipulate that to create cheats, to give you an unlimited amount of lives, etc. One interesting use case that you might see in the product development world is maybe you are trying to steal your competitor's software or their like secret sauce, if you will. You could try to reverse engineer your competitor's software to understand what they're doing so you could do the same thing. And another one that you'll likely be familiar with already is bypassing copy protection. If you've ever downloaded cracked software offline, somebody reverse engineered it and found out how to neutralize the license check, etc. Also, for everyone on Zoom and in person, if you have questions at any point, just raise your hand. I don't think that this presentation will go over time. So if you're confused, I'd rather just answer the question as we go. So if you want to start diving into reverse engineering, you'll need a little bit of background in some computer science related stuff. I expect that most people here will probably have this. If you've been in the computer science track, you've likely taken a programming class where you've done C++ at some point or C. And if you know the fundamentals of pointers as well, that's helpful for understanding how a lot of stuff works. If you're already familiar with assembly language and stuff like the stack and the heap, even better, but that's not mandatory for today. So one thing I will say is that reverse engineering is not the most beginner friendly topic. It's pretty difficult to get into at first, and the learning curve is pretty steep. An hour isn't enough time to go over everything you need to know about reverse engineering. So this is kind of going to be an overview type talk to get you guys interested. If you don't already know what reverse engineering is, maybe teach you about, something new. But if you want to get into reverse engineering, you'll definitely need to, put some time in on your own. That being said, once you get to a point where you know what you're doing, it can be very rewarding and very fun. So if this does seem interesting to you and you go home and it's super difficult, just stick with it. Ask questions in the Discord. There's plenty of people here who'll be willing to help you out. It's just something that takes a lot of practice. So the easiest way to start talking about reverse engineering is think about what forward engineering is, or just engineering, I suppose. In the context of writing software, you would write source code, and then that gets put into the compiler, which gets eventually turned into assembly, and eventually machine code, and that's what you get at the end. You run that machine code on your computer, that's your program. Given that understanding, you would probably jump to assume that reverse engineering is just switching the order of those things to go backwards, which is not correct. So this doesn't work for a number of reasons. Compiling code, when you put your C code into the compiler and you get out a program, that's a destructive one-way process. There is a lot that's going on. This slide from this diagram here is very oversimplified, as I point out in the slide title. There is a lot of stuff that goes on here. So there's a reason that you can't just reverse those steps. You will inevitably lose tons of information as you compile a program, which makes reversing this process trivially not possible. And it is impossible to recover the original source code for programs that are from compiled languages. Good example is you can't turn steaks back into cows. So if you've done any C programming before, hopefully this function doesn't look super scary. This just takes an array of floating point numbers as a pointer, and then goes through and computes the average of all the numbers that it's given. Takes a input and a count parameter. Pay attention to the names of variables here. Look at the structure. We can see we have a for loop in the middle, and then this final division at the end. This is kind of a cheating example because most of you won't know what this is yet, but this is what happens after you compile that, to ARM at least. So it should be pretty apparent that this does not look anything like the input. You will notice that there are no variable names, there are no control flow statements, no real indication of what's going on here. And if you don't know how to read ARM assembly, then this isn't particularly useful. So like I said, all of the information for you as the programmer that you might rely on when writing code goes away because the computer doesn't need it. That information is for you. The computer just needs instructions and it does what it's told. So why put that information into the program? As a result, all of that's gone. And this is part of the reason why you can't just turn a compiled program into source code, because how would you be able to do that if you don't have all this supporting information? Knowing what we know now, you think about this again, we're not going to be able to take a compiled program and turn it back into its original source code. So a revisited idea of what reverse engineering looks like might be something more like this. We can take our compiled program, which we receive in the form of machine code, and we can disassemble it and get assembly. And then through some human effort and using different tools, we can eventually reach an idea of what that program is doing. But once again, not a carbon copy of the original. So I'll dive into some of the more technical side of this. One thing that you will hear people talk about a lot with reverse engineering is people will say, oh, send me that binary or open this binary. In this context, we're not talking about a numbering system as much as we're talking about a big collection of bytes. So that's exactly what a binary is. It's a big collection of bytes. You know, you've seen binary files before. Have you ever seen a .exe or a .dll, .dylib, whatever? All types of binary files, and they have code inside of them. And that's, once again, just a blanket term to kind of refer to all of these. What's in a binary? So everything that the program needs to run gets thrown inside of the binary. So the actual code itself, as well as global variables, other things that get used in the course of the program executing, are all included in there. There's some information for the operating system as well, so that your computer can actually run said binary. And they come in a couple different flavors. On Windows, you have your PE, your portable executable. On Linux, you have your ELF, which I think stands for executable linkable format. On Mac OS, iOS, all the Apple stuff, you have Mach O. These are all solutions to the same problem. It's just a way of organizing information in a program where that information is code and other data. Another major thing to understand, which, how many people here have taken computer organization so far? Decent chunk, halfway, hand up in the back. So your computer operates on instructions. An instruction is equivalent to the atom in the world of code, if you want to think of it that way. An instruction is a primitive operation which tells the computer to do something, such as add two numbers, load something from memory, put something in memory, subtract two numbers. In series, these become meaningful. And like I said, it's the smallest amount of code that you can really break down into one piece. And these come in different forms. So right here, this 31C0 happens to be the encoding for XOR EAX in x86 assembly. That's the machine code representation. Instructions can be encoded as bytes. That's what your computer actually sees and runs. For humans, if we want to read or write assembly, we usually do that with assembly mnemonics. So this XOR EAX, and this are the same exact thing in two different forms. Pay attention on this slide, because we're going to do something after this that requires the information. So most of these are pretty simple instructions. Move is equivalent to like left-hand side equals right-hand side. So move XY just sets X equal to Y. And this is for x86 for context, but move X, and then if you see the little brackets, that's kind of like the brackets in C where you dereference a pointer or you index an array. That sets X equal to the Z index of Y. Add is pretty self-explanatory. You add Y to X and store the results in X. Compare does a comparison. And then after, we have our jump equal and jump not equal, which will jump to the address of Z, depending on whether or not the previous comparison was true or false or not equal equal. Some instructions have multiple forms. This is a super oversimplified example, but this is like the minimum working amount of information for the example coming up. Before I move on to that, does anybody have any questions about this? Nobody on Zoom? So this is not meant to be indicative of like what reverse engineering always looks like, but I'm going to kind of illustrate what reverse engineering a function may look like if you're trying to reverse engineer new code. If you already know what this is, don't shout out the answer just yet. I'll ask in a couple of slides. But this is a function that most of you have probably used before. You've just never seen this in assembly form. And this is x86 assembly. Unless you have a iPad or a M1 Mac, this is what your computer runs. And I should note that this isn't completely valid x86, but I made some modifications so that this is more palatable. I've given the function prototype up here. So this normally wouldn't be provided to you if you're reverse engineering, but I'm adding a little more context. So we have a character pointer or a character array coming in via RDI. We have a character pointer coming in via RSI and an unsigned long coming in RDX. And when you see these in the assembly below, you can think of these as just variables. So when you see compare RDX is 0, RDX is a variable that came in as an argument. So where would you start if you saw something like this? Because this is completely valid code that you might come across. I would personally start by identifying these labels here. So even if you don't happen to know what any of these functions do, or any of these instructions do really, and you probably don't know the context of everything here yet, we can find out a little bit of what's going on just by looking at the labels. So immediately we have a compare here, and then we jump to label 2 if that comparison was equal. Label 2 puts us straight to a return instruction. So that kind of sounds like an exit condition or somewhere we go when we're done. On the other hand, if we fall through in assembly, if your jump fails or if your jump is not taken, you just move on to executing the next instruction. So if you fall through, we keep executing here, and we can see that down here we make a comparison, and if it's not equal, we jump back up. This smells like a loop, and you'll come to know that the more you reverse engineer, but this is typical kind of like for loop or loop structure. Easy win we can make immediately is renaming some of these labels to something that makes a little more sense. We still don't know what's going on here, but we've identified a loop and we've identified an exit condition. And this is something to keep in mind when you're reverse engineering, because when you're reverse engineering software, very rarely are you going through every single instruction in the program, because that your program will contain hundreds of thousands, if not millions of instructions. Nobody has that kind of time. Being able to identify quick control flow elements like this is very important. So looking at your jumps, looking at your branches is a good way to make quick wins on finding out what a function is. Next thing we can do is we can annotate some of the basic operations that we know. In assembly, most assembly languages, everything after a semicolon is a comment. So that's what I've used here. We went over what our move and add instructions do. And those just set, in this example, we set RAX equal to 0, and then we increment RAX by 1 down here. And return, the ret instruction does a return. That one's pretty self-explanatory. From there, we can kind of look at what our conditional branches look like. So this compare RDX 0 here, we're just asking if RDX is equal to 0, do something. In this case, that something is go to the finish label. Same down here. If RAX is less than RDX, we're going to go to the loop. Now, this is actually a jump if not equal, but you can see from this add here that by continuously adding and then checking if it's equal, we're essentially checking if it's less than. Last thing we can do is annotate our memory read and write here. So this little part of the code here, we are loading, or actually, does anybody remember what the square bracket syntax does? Gabby? Okay, so yeah, the square bracket is indexing memory, basically. And our first argument is going to be the base. So in this case, we're taking, I guess I had it in the comment here, I kind of forgot about that, but we're taking the RAX index of RDI and storing it in RCX. Immediately after, we're setting the RAX index of RSI to the value that we just took out. Before I proceed, does anybody have a guess as to what this function is? This is a function that you've used before hundreds of times, directly or indirectly. Scott, anyone besides Scott? You. This mem copy? Exactly. This is mem copy, or I just called it copy buffer because this isn't the official mem copy implementation. But this just copies, this is memcopy in C. It copies all of the data from one buffer to another, and you give it a size, source and destination pointer. So I've renamed these arguments, and I've included the register that they're passed in. This is what the function looks like after we went through and reversed all of it. So if we try to translate this to C, which if you look at what we have on this slide here, we basically have all of it laid out in front of us already. So if we translate this to C, we get a function that looks more or less like this. And if we compare it to the original source code, that's pretty close. We didn't get it entirely, but they functionally do the same thing, which raises a good point, which is that source code never translates directly, one-to-one to assembly or anything like that. Also, assembly is not immediately readable. If you've been doing this for a long time, maybe you would have breezed through the first slide and known what it is immediately, but it still takes some time to read assembly and decipher what's going on, and that's important to keep in mind. Another thing is that compilers can change the shape of code, if that makes sense. So in our reverse code, we had this while loop, and in our original code, we had a for loop. In this context, they do the same thing, but it's important to remember that the compiler is free to change the structure of your code however it sees fit. In this case, I actually compiled that with size optimization on. So if you compile with GCC or Clang and you pass the -oz argument, it will try to compile it for the least amount of bytes, which is helpful if you're trying to fit all of it on a PowerPoint slide. To conclude, though, we got an idea what that function does. In this case, someone was able to identify it, and we found out that it was just effectively memcopy. You can learn a lot by just disassembling and reading through the source code or the disassembly of a program. And while we didn't get the original source code, we got something that was very similar to the original. So that was meant to kind of be a little exercise of what reverse engineering might look like. Obviously, you'd be doing this on a much larger scale when you're reverse engineering an entire piece of software or something, but that was meant to illustrate what assembly looks like and hopefully get you a little bit comfortable with reading assembly and trying to make sense of it. From there, I'll talk kind of about the tools that you'll typically use as a reverse engineer. The one that you'll probably use the most often is your disassembler. We've been talking this whole time about taking machine code and turning it into assembly. That's actually a harder task than it might sound like. So your disassembler is going to be responsible for, taking a program that you give it, picking out all of the bytes inside and identifying functions and parsing imports and all other sorts of crazy stuff, and giving you something that you can actually look at and be productive with. So your disassembler will turn the machine code back into assembly that you can read, and almost all of them will also help with identifying control flow. Some of them might show you the code in the form of a graph so you can visualize the execution. Lots of them also include a quote unquote decompiler. It's a term that I put in quotes because, as we previously discussed, it's not possible to decompile a program. You can't take assembly and then turn it into the original source code. And so these decompilers that you'll find in tools, will turn it back into pseudocode and try to make the best sense of it that it can of the assembly and produce some sort of C-like code usually as a result. It's important to keep in mind that that's not actually turning it back to the original source code. If you know how to do that, let me know. So your popular disassemblers, if you're looking to get started, are going to be IDA Pro, which is the kind of industry standard, if you will. IDA Pro has been around for longer than anyone in this room has been alive. I think it first came out in 1991. So IDA Pro is pretty tried and true. It's the oldest and most popular disassembler. On the other hand, we have Binary Ninja, which is a more modern and newer disassembler that only came out 6 or 7 years ago now. Takes a little bit of a different approach to how it does analysis. And then which is by using intermediate languages, which is a conversation for another time. But there's also Ghidra, which started as an internal NSA tool in the early 2000s and is now free and open source for everybody. So that's probably a good pick if you're just wanting to get started, because you can, go download it right off GitHub and start there. And there's a lot of good resources for Ghidra out there as well because of it being free. It's, gained a lot of popularity. Another helpful tool that you'll want to use is a debugger. Disassemblers are what we refer to as, or we talk about static analysis when we use disassemblers, which means that you just throw the program into the disassembler and then you read through and you try to make sense of it and you do your work, but never during that time is the program actually running. It's similarly just like trying to find out how code works by only reading the source code and not running it. On the other side, we have debuggers, which let you run the program, but let you screw around with it as it runs. So a lot of you have probably used a debugger, I would assume, during your programming classes. Yay, nay? Okay, so you've used a debugger in a programming context. We can use the same exact tools for reverse engineering. Granted, a lot of the luxuries that you probably had, like being able to see variable names, you won't have this time around, but the core debugger features remain. You can pause a program wherever you want. You can change values in memory. You can tell it, go here instead of go there. You kind of get to play God as the program runs and make it do whatever you want. And this can be helpful for understanding how the program works, because you could actually jump into a for loop, for example, and go through every single step and watch what it does to try to find out what it's doing. And like I said, these are all going to be tools that you use as the program is running. As far as debugger choices go, there's kind of less options in this space. So GDB is the standard debugger on Linux. If you're going to be playing CTF or doing any of your like hack the box, that kind of stuff, that's what you're going to be using. That's just GDB is the debugger on Linux. You can also run LLDB, which is available on Linux as well. It's less popular. It's kind of the standard debugger on macOS and iOS and the rest of the Apple platforms. And the first two, I believe, actually do work on Windows, but have fun with that. I wouldn't expect them to work out of the box. WinDebug is Microsoft's official Windows debugger. So if you're doing Windows stuff, that wouldn't be a bad place to start. Although there are more choices on Windows. There's x64 debug as well, which you might like better. Give them a shot. WinDebug is the only debugger on Windows that can debug the kernel, though. So while you probably won't be jumping in there immediately, if you ever want to do kernel reverse engineering or stuff like that, then having WinDebug in your toolkit will be helpful. So one thing to think about is like, where might you go with this, right? Now, I do this primarily as a hobby. I think this is interesting, so I do it. But there are definitely careers where you would be applying reverse engineering knowledge. Two of your big ones, these are by all means not the only reverse engineering jobs, but these are easy to talk about. Vulnerability researcher. There are plenty of companies that are hiring vulnerability researchers, and not just companies, but defense contractors, the US government itself, who are looking for people and employ people full-time to look for vulnerabilities in programs. If you've heard in recent news about like different countries using exploits on iPhones to try to, sneak into people's phones and get their data, etc., that's obviously not a feature that Apple provides by default. You have to do that by means of reverse engineering, finding an exploit, and then exploiting that exploit such that you can achieve remote code execution or put a payload on someone's phone, etc. There are plenty of jobs in this where you will be analyzing software, looking for vulnerabilities that you can successfully exploit, and then you may even be writing those exploits as well. Another big one is being a malware analyst. So similarly, there's plenty of malware out there on the internet. There's kind of a cat and mouse game between malware authors and antivirus companies. So there are definitely antivirus companies that employ reverse engineers to reverse engineer malware, develop new tools to identify malware. And there are other just cybersecurity companies that will employ malware analysts as well to learn about how malware is doing what it's doing, how it might be evading antivirus, etc. Where can you go from here? So like I said, this was kind of meant to be an interest garnering presentation. I've done this in the past where I've put people to sleep talking about x86 assembly instructions, and that doesn't usually work well. So reverse engineering is something that you definitely have to get your hands on to learn, and you'll have to do a little bit in your own time to really start understanding how it works. There is the CTF route. If you're not familiar with CTF, capture the flag already, you can talk to Scott about that, but CTF is online competition that happens, there's plenty of them every weekend, and there's usually some sort of reverse engineering related challenge. There are also plenty of Crack Me challenges online, which are essentially little programs that are meant to be reverse engineered and then patched such that you can get to the win message effectively. So maybe there's a hidden password, maybe there's a key algorithm that's hidden in there, etc. Those are great. I personally don't do a ton of CTF or Crack Me challenges because I don't find them as engaging. So one way that might make this a little more motivational for you is if you put something on the line, right? I mentioned earlier that cheating in video games requires reverse engineering. Maybe you have your favorite video game. Maybe you're also not very good at it. You could try making cheats for your favorite video game. That will require you to reverse engineer the game, learn about how it stores data, maybe even learn about how its anti-cheat works, etc. There's also cracking software, which you should only do on software that you already own. That's another fun one as well. And in both of these scenarios, there's kind of a reward at the end, because if you manage to create cheats or crack software, well, now you're left with something that you can use. There's also plenty of books out there. I don't have any specific recommendations, but if your style of learning is reading and then applying that knowledge, there are plenty of great books. If you're looking for something a little more palatable and not as long-winded, most CTFs, people will post write-ups at the end about how they solved a challenge. So if you were trying to reverse engineer something and you got stuck, you can read the write-up of how somebody else solved it and learn, maybe they identified something that you didn't. This is kind of a rehash of what I just said, but there's an infinite amount of resources on the internet for learning reverse engineering. So there's definitely no shortage of things that you can find online to help you learn about this. The Reverse Engineering for Beginners book is quite good. It's also 1,500 pages. I would recommend, it's very great content if you have time to read it. And you obviously don't read it all in one sitting, but you could start reading that. One website, which we're looking good on time, so maybe I'll show this a little bit in a moment, is Compiler Explorer. I've given this tremendous praise the past 2 times that I've done this presentation, but Compiler Explorer is a great website for being able to watch how C or most other programming languages actually turn into assembly. Now, obviously that's part of the forward engineering process, but if you're able to see how a compiler kind of thinks, how a for loop turns into assembly, that will help you when you're going the other way around. If you see a for loop in assembly, you will know how to identify that when you come across it, and then be like, oh, this is a for loop, or this is memory indexing, etc. Already talked about Crack Me challenges. Live Overflow on YouTube, if you're not familiar with his channel, is very good content, and most of it is beginner friendly as well. I would highly recommend watching some of those videos. And finally, the UFSIT Discord server. There's plenty of us who do this for fun, or know a thing or two about reverse engineering. So if you're looking to get started, you have questions, or you're stuck, come ask questions. Speaking of asking questions, that's the end of my presentation. So if you have questions, now would be a good time. I can also show Compiler Explorer, other stuff, or everyone just wants to leave, we can do that as well. Any questions? Compiler Explorer.
What's your favorite ARC64 instruction?
Huh?
Your favorite ARC64 instruction?
Right. All right. So I'll show Compiler Explorer for just a moment, but I won't do it as long-winded as I have in the past. So this is Compiler Explorer. Is this easy to read on the TV, or is this a bad color scheme? How's that? Better. Okay. So pretty simple website. You write C or any of these languages on the left side, and you get assembly on the right side. For languages like C, which have multiple different compilers, you can choose your compiler, you can choose your target architecture, whatever. You can also, huh? I'll show Rust code in a moment, but you might regret asking. So the other thing is that you can highlight these lines here and kind of see which lines translated into what assembly. So like I said, I'll save you from my normal rants about this, but Compiler Explorer is very useful for understanding how, it's very important to understand how code turns into assembly if you wish to understand how to take assembly and make sense of it in the form of code. So spending some time on here, you know, if you come across something and you're not sure what it is, and you can try to start writing something similar in C, or if you're just curious, oh, how does this work? I use this website all the time just because I'm like, oh, I don't know how this translates to assembly. Let me check. So I found this to be very helpful when learning assembly, which is going to be a part of your reverse engineering journey, wherever that may be. You will need to learn an assembly language for whatever you're reverse engineering. So getting started with this and just playing around and slowly becoming familiar with how different instructions work, how different things get turned into instructions, etc., is very valuable. That is about it. So if there's no more questions, I guess we are done here. Huh? Oh, Rust. Rust gets a little scarier the more you go, because Rust inserts a bunch of random stuff. I will say that if you're doing this because you want to get familiar with an assembly language, even if C is not your favorite assembly language, I would recommend writing in C on the left side, because C translates most directly to assembly. Languages like Rust, which have, you know, where they're going to check if a number overflows, etc., for your learning purposes, are going to be inserting garbage into the assembly, which isn't really helpful to you. C is probably the most literal and, you know, clean translation as far as, you know, source to assembly goes. So that's a good place to start if you're looking to understand how code gets compiled. But certainly, you know, if you're looking at a Rust program that you're trying to reverse engineer, yeah, look at how Rust gets compiled. Huh?
Is there like a different compiler option that makes it less full?
Yeah, you do have a choice of compiler depending on what you're looking at. So if you look at something like C, you can choose between GCC and Clang, and you can even pick like Clang ARC64 or whatever. But Scott,
Do you put on O3?
huh?
Do you put on O3?
Yeah. You can also set compiler flags up here to compile with optimization or not, which you might want to see how stuff gets optimized. One thing, especially on x86, if you're reversing x86 code, is doing a division by 7, for example. might actually be mathematically equivalent to like shifting a number to the right by a certain number of bits and then moduloing with a different number. Some compilers like to change your division into weird, bit operations because it's faster. If you see something crazy sometimes, it might just be optimized division. And if you compile some C code with optimizations on, you might come across that. But that being said, I think that's the end of my compiler explorer rant. And it seems like we have no other questions. So I'm gonna go ahead and shut down the Zoom meeting. And I think we are done here.